she's from the Instituto de Matemáticas de la UNAM, and she will tell us about the three-dimensional loop-erased random walks.
Well, thank you very much for the invitation. I'm also very happy to be in this very international seminar. It's great that you have this initiative. So I'm going to tell you about three-dimensional loop-erased random walks and their scaling limits. And well, it's a scaling limit. And this is mainly, well, the main result that I want to talk today is joint work with Shinji Lee at Peking University and Daisuke Shiraishi in Kyoto. But in some part, I'm also going to touch on some work with other collaborators, so with Omar Angel at UBC and David Croydon, also at Kyoto University, and a couple of PhD students from Shinji, Runsheng Liu and Xiangyi Liu, both at Peking University. So more or less, this is the outline for today's talk. So first, I'm going to talk about loop-erased random walks and introduce the model. And my main goal is to show you the role that play one-point estimates on understanding the growth exponent of the loop-erased random walk. It's a scaling limit. The main result for today is the existence of the Minkowski content for the scaling limit. And then what are the results that we can derive from getting the existence of the Minkowski content for the scaling limit. In particular, that we get a convergence in the natural parametrization. And all this in the three-dimensional for the three-dimensional loop-erased random walk. So for a one-point estimate, what I mean is in the discrete, the probability that a given point is part of the loop-erased random walk trajectory. But in the continuum, we can also think about the probability that for a given point and a very small ball, that the scaling limit that we're going to denote by k intersects this small ball. So we have estimates both for this one-point estimate on the discrete and this small ball intersection estimate on the continuum. And then as well, these results are interesting on their own, but they also have consequences for models that are related to the loop-erased random walk. So in this case, as maybe you have heard me talk about this before, I'm interested in uniform spanning trees. In this case, a three-dimensional uniform spanning tree. So we are also look on some of the results that we get now that we have all this work for the loop-erased random walk now on the uniform spanning tree. So that's my plan for today. So let me start with the definition of the model. And loop-erased random walk is very simple to define. So we start with our beloved simple random walk. So here I'm able to draw set 2, but we can define this on set D for dimensions D larger or equal than 2. And but we are mainly going to focus on the three-dimensional case. So we are on the lattice and we are going to fix a ball of radius m. So we consider a simple random walk starting at the origin, and then this is going to be a stop once it reaches the boundary of this ball. So this happens now. So this is the first arrival to the boundary of this ball. So then the loop-erased random walk is just the loop erasure of this trajectory that we have realized. So with this erasure of the loops is done chronologically. So essentially, one way to think about this is that starting from the origin, we can take the last exit edge and then erase, this first loop that appears. So we are just going to take this last exit edge, and for the following vertex, we again consider the last exit edge. Again, in this case, there are no loops, so we don't have to erase anything. So at the end, we erase all the loops in chronological order, and what we obtain is a simple path starting from the origin to the boundary of the ball of radius m. So for loop-erased random walk that reaches this Euclidean distance m, I'm going to denote it by gamma n. Well, this is a model that has been studied intensively since its introduction by Greg Lawler in the 80s. So in the three-dimensional space, realization of the loop-race random walk will look like this. So here I have both the simple random walk and the loop and its loop erasure. So the loops that are erased are in blue, and what we are going to keep is just the orange path. And one of the reasons this has been so studied, it's because first is related to the simple random walk, so it's a tractable model, and a lot of properties, as we're going to see, of the loop-race random walk can be described in terms of non-intersection probabilities of simple random walks. And also it has the behavior it has behavior that is common of critical lattice models. So it allows us to understand this critical phenomena in a tractable way. So, this is the way that I defined my loop erasure, but now we're going to look at the scaling limit. So for doing that, it's going to be more convenient to, instead of rescaling the ball, I'm going to rescale the lattice. So the lattice is going to be rescaled by this factor 1/m, which is equivalent to having a ball of radius m. And then the ball is going to be fixed as the unit ball. So all the random trajectories that are going to appear as I rescale the lattice are going to live on this compact ball in the three-dimensional space. And you can see that as we make our lattice more finer, we get something a more interesting behavior, and then we are going to look at what happens at the scaling limit. So this is this object that Gary Cosma proved that it exists. In his honor, we are going to denote it by K. So our goal is to understand the properties of this scaling limit and to see and to prove the stronger, a stronger way of convergence towards K. So now let me tell you about what we know for these 1-point estimates. So we have estimates for both for the discrete loop-race random walk and for this scaling limit K. So the first quantity that we need to have in mind is the growth exponent. And I already promised that the growth exponent it's related to the 1-point estimate, and this is very simple. So consider now the loop-race random walk, but in this case, we are going to think about the infinite loop-race random walk, one that is not a stop when we reach a given ball. So for any ball of radius n, we can ask how many steps are needed so that we reach that Euclidean distance or extrinsic distance m. So this is the number of steps that are needed so that this norm is at least n. And then the growth exponent is defined as, this exponent that describes the asymptotic behavior of this random variable mn. So in the way that, it can be precise on several levels, but essentially we want to say that the expected value of mn is hopefully asymptotically equivalent, but it could also be on a maybe not as detailed as we can have different levels of how sharp are these estimates. But the point is that the exponent that controls the behavior of this mn quantity is beta, this growth exponent. So essentially it's telling us in the large scales how we have to rescale our number of steps so that we can reach distance n. And the first dimension on which this was studied and understood pretty well was in the two-dimensional case. So that's why I'm focusing on this slide on this two-dimensional result of Rick Kenyon. And he proved that the growth exponent for the two-dimensional loop-race random walk is 5/4. And this is Very beautiful result because it uses the relationship between the loop race random walk and the uniform spanning tree, and also domino tilings, and well, very beautiful bijections that are only available in the two-dimensional space. Well, on set 2 particularly. So what Rick proves is that this this 1-point estimate of what is the probability that a given point inside this ball belongs to this infinite loop race random walk. So here, I apologize. So, well, this n is this r over here, so the radius of the ball. So here, the probability that one of these points belongs to the loop race, infinite loop race random walks scales in this way. So the exponent for the 1-point function for the loop race random walk is 3 over 4. And essentially, when we look at this expected value of Mn, given that we are thinking, we already know that this is a simple path. There are no self-intersections by construction. So every point that is going to appear in our path appears only once. So essentially, this is just linearity of expectation. So we only need to see how many points are part of our path. So we have that this growth exponent is the dimension minus the exponent that is related to the 1-point estimate. So that's where this 5 over 4 comes from. And well, this is a relation that is satisfied in all dimensions. Once we have the exponent for the 1-point estimate, it is very easy to obtain the growth exponent. And then the work is to make this asymptotic relation as precise as possible. So that's part of the work that was done in 2 dimensions. And in parallel, there's also work on understanding the scaling limit of the 2-dimensional loop race random walk. And this is our most successful story. And in a sense, it gives us the pathway of what we want to do in the 3-dimensional case. So the first result that I already explained is the existence of the growth exponent, and that it has this very nice value, a fraction. But at the same time, a lot of development happened, and Odette Schramm introduced the Schramm-Lohner evolution in 1999. And then a couple of years later, together with Greg Lawler and Wendelin Werner, they proved the convergence of the 2-dimensional loop race random walk to SLE2. And well, the point is that this convergence was improved over the years. So the original result was for topology for curves that did not choose a specific parametrization, but compare like all the paths, and the distance between those paths was with respect to the best reparametrization of the paths that allow them to be closer. So in a sense, in this result of Greg Lawler, Odette Schramm, and Wendelin Werner, there was not a preferred parametrization, but it was more about having a direction and the shape of the path. And of course, from the construction of SLE, there was a parametrization that is given by this half-plane capacity of SLE. So it means that it's a conformal way of parameterize the curve, but that doesn't have to relate to the way that we construct loop race random walks on the discrete lattice. So there was some work to understand what would be the best way to parameterize these loop race random walks that we define on the lattice, and what would be the natural way to parameterize its scaling limit. So this is in 2 dimensions. This was done by Greg Lawler and Frederick Biglund, together with work on what would be the correct way to parameterize the scaling limit, so that it keeps this relationship to the discrete lattice. So, maybe I would need another a figure, but let me explain maybe just with words. So if we are on the lattice, the idea is that each time that we cross an edge, we want to do on a time that is proportional for all edges. So we don't want to, so this natural parametrization is just a parametrization that is given by rescaling the lattice. And the natural way to rescale the lattice would be given by the growth exponent. But then we also want to parameterize the scaling limit, so the object that we obtain by the end. So there are two ways to do that. So we can just keep this parameterization that we have from the discrete object and take the scaling limit and obtain the limiting parameterization. But in a sense, that's a little bit like cheating because we are just carrying the parameterization that we obtain from the discrete object. But we also want it would be better to have a parameterization that is intrinsic to the object that we obtain from the limit. So one way to do this is by parameterizing the limiting object, in this case, the Schramm-Lohner evolution of parameter 2 by its Minkowski content. So essentially, the Minkowski content defines a measure, and this measure over our path is going to increase as we go go over the path. So as increasing the measure means that we are increasing time, and that's how we parameterize this limiting curve intrinsically by its Minkowski content. So this is going to appear again, but I realize that it's not something that is completely explained. So I apologize for that, but we'll go back to these ideas. The point is that this was done in 2 dimensions and little on the path that we want to do in the 3-dimensional case as well. And for showing the existence of this Minkowski content and proving the convergence in the natural parameterization, an essential ingredient was a strong estimate of the one-point function that was also developed by Benesch, Lawler, and Bicklund. So here they show that this one-point function is asymptotically equivalent to a constant that they can also compute in a precise way times r minus 3/4, which is our exponent. And the downside from this 2-dimensional story is that it relies on that on a very good understanding of who is the scaling limit, which is the Schramm-Lohner evolution, and that we have conformal invariance and all these nice properties that we have in 2 dimensions that are not available in the 3-dimensional case. So for example, in this strong estimate for the one-point function, they really work in the continuum so that, the reason why they can compute this very nicely is because everything is in terms of some conformal mapping, and this can be computed precisely. But once we go to the 3-dimensional space, as it's the goal of this talk, these tools are no longer available. So for comparison, let me show you what happens with the scaling limit and the one-point function for the loop race random walk as we change the dimension. So I already talked about the 2-dimensional case. Here the exponent, now it's an m, so it's the new radius. We went back to an m, is minus 3/4, and the scaling limit is the Schramm-Lohner evolution. For high dimensions, it was shown in the very beginning, in the introduction of the model, that the scaling limit is Brownian motion, and the one-point function, it essentially scales as a simple random walk, 2 minus the dimension. The upper critical dimension is 4, and again, it scales to Brownian motion, and then we can see the log correction when we look at the one-point function. So this result that this scaling would be m to the minus 2 and some log correction was known, was proved by Greg Lawler longer before than 2016. But in this paper of 2016 is where they obtain also the exponent here on the logarithmic correction. And our goal today is to see what happens in dimension 3. So the scaling limit is this object K, which is a little bit mysterious and hard to, we don't have a description of K that is directly in the continuum. We always access K through the limit. And the 1 point estimate that we have is that it is the growth exponent minus the dimension, as it is expected from this computation with just the expected value of the number of steps that takes a simple random loop race random walk to reach the boundary. So you can see that this is, well, it depends on what is the value beta, but it turns out that this, well, exponent does not correspond to this behavior that is in this Brownian regime. And this limiting object is not Brownian motion, but we do not have construction as in the Schramm-Leuner evolution. So it's something that we have to treat in a different way, and that's why, well, I think it's a nice object to study. So let me tell you about this story of how we have come to understand this limiting object K. So as I already mentioned, this was fantastic and very, very long paper of Gary Cosma, where he shows that there is a limiting object for the three-dimensional loop race random walk. So the framework that he in which he studied this object is a polyhedron. Let's think of a cube, and then we consider our rescalings of our lattice. This set 3 rescaled by a factor of 1/m. And then we can consider the loop race random walk on this lattice until it reaches the boundary of this polyhedron. Here it should be Pm. This index is wrong. And there is a reason why it's wrong. In the way that it's written on the paper is that if we look at the dyadic scalings, then Gary proves convergence in law to this some limiting object K with respect to the Hausdorff metric. But in the paper, and this is kind of the main result of this paper, Gary shows that this limiting object K is a scale and rotational invariant. So the scale invariance is kind of by construction. By the main point is that it's also rotational invariance with respect to all rotations of R3. And from this rotational invariance, if one I'm inside of this paper, in between all the lemmas of his 90 pages, one can actually see that this convergence is not only over the dyadic scalings, but over for any gamma m. But the restriction is that this convergence is with respect to the Hausdorff metric. So this is a metric that compares inside our cube or our polyhedron compact subsets. So essentially, this convergence is for the shape or for the trace of our loop race random walk. So we don't have any parametrization. And at this point, there's still some work to do to see that this limiting object can also be described as a simple curve. So this is something that Artyom Sapochnikov and Daisuke Shiraishi proved 10 years later. So this limiting object comes from random simple curves, and almost surely K is a simple curve as well. So then we can consider some parametrization for K and hope to improve this convergence that is no longer just for the trace, but also for a real metric for parameterized curves. So, well, to hope to have this convergence in some metric, we need to parameterize in the right scale, and that's what the growth exponent does, because it really essentially what it tells us is how many steps are required so that we can reach distance n. So when we rescale our lattice, essentially our steps are of size 1/m, and then we want to reach distance 1. So essentially we want to get extrinsic distance n. Daisuke Shiraishi proved in 2013 that there exists some exponent beta, and these bounds were already known by previous work of Greg Lawler. So beta is larger than 1 and smaller than equal than 5/3. So that this expected value is n to the betas plus some correction in the exponent. We don't really know like the exact value of beta. David Wilson did some simulations that lead us to believe that it's not going to be a nice rational as in the two-dimensional case. And we also, all this simulation lead us to believe that it should be closer to 5/3 from this computational analysis. But we don't have really a proof yet for sharper bounds for this growth exponent. But the point is that it exists, and in this paper, again, what he shows is that this 1-point probability is decaying as m to the beta minus 3, and then the correction of this exponent. So then this is the estimate that allows to do a lot of the following work, including getting what is the Hausdorff dimension of this limiting object, which is, this is not surprising, is beta, which is essentially telling us how many vertices in the limit, how many points in the limit, how many boxes in the limit we are going to occupy asymptotically. So with these estimates, Shinjili and Daisuke Shiraishi, in a paper that first appeared in 2018, but I believe that was finally appeared on PTRF this year. They show that that's enough for getting convergence in the natural parametrization, but with the following caveats. So we have that beta is this growth exponent for the three-dimensional loop race random walk, and then we consider this loop race random walk at this scale on the lattice 1/m set 3. And now we are going to look at just the trace, which is the object that Gadi Cosma proved that converges weakly with respect to the Hausdorff distance. And then this is the object that we are going to parameterize. So the way to, this function fm is just this parameterization. This is a factor for our parameterization. And as you can see, it is in terms of the 1-point function, but for a very specific point. So this x hat m, and this should be like written somewhere here, is not just any point inside the ball, but it's the point with coordinates 1/2, 0, 0. So it's essentially somewhere here. So this factor that depends on our scale m is scaling with respect as the probability of that the point 1/2, 0, 0 is part of our loop race random walk path. And then, this is giving us the, by multiplying by this factor m cube, this is giving us the growth exponent estimate. But we cannot really scale by m to the beta. We need something that is a little bit sharper. So this does the job, this 1-point estimate for a fixed point. And then we consider a measure that is the occupation measure of the trace of the loop race random walk at this scale m, rescaled by the inverse of this factor that is in terms of this 1-point function. So essentially, now we have the trace together with a parameterization. So this gives a parameterized curve, and the result is that this converges weakly jointly to this the scaling limit that we already know for the loop race random walk k, and some limiting occupation measure mu. So this is our the first approach to having this convergence in the natural parametrization. So here we are just saying we're going to parameterize in a way that every time, the time that we need to cross a vertex is going to be constant and is going to be rescaled as this factor well, the inverse of this factor Fm. But the problem is that this, and then we obtain the limiting result. But the problem is that the way that we parameterize this limiting object really is coming from the way that we decided to parameterize our loop race random walk. And on the discrete, this is natural, but on the continuum, it really, we could have something more satisfying. So just to clarify the way that this weak convergence is in the topology generated by this metric. So, well, the point of writing down which metric is it, these are two curves, lambda1 and lambda2. And here, this curve lambda1 has some length or duration t1, and lambda2 has some duration t2. So essentially, we're saying when two metrics are close, they have a very close length. And also when we traverse these curves, they are also going to be very, very close. So here we're comparing both the lengths of the curves. They do not have to be equal, but but when this distance is small, they are going to be very close. And also, as we traverse these curves, they are going to be close to each other. So at least in this result from Shinji and Daisuke allow us to really compare these two these discrete curves and its limiting object in a real topology for curves. But we have these places for improvement. So we want a better parameterization. And another place that we can improve is that, well, our scaling factor is in terms of this quantity, this 1-point function for a given point, that point with coordinates 0.5, 0, 0. And it would be better to have like a sharp estimate for this quantity. So for dyadic scales, Shinji and Daisuke had a result in a different paper that gives a sharp result, but only over dyadic scales. And the reason is that they have this sort of shield argument over exponential scales, and that's why they have to restrict to that. So if one doesn't, if one restricts this convergence over dyadic scales, then this factor Fm can be improved. And it's just going to be m to the beta, and everything is going to work fine. But so the way to improve this factor, is to obtain something similar sharp estimate, but that is not restricted to dyadic scales, but for any scale. And as a consequence of having this strong 1-point estimate, then we can also talk about the Minkowski content of the limiting object. So this is a result that appeared on the arXiv last year. So this is both for ball hitting probabilities for the limiting object and for the discrete loop race random walk. So, well, I'm going to show both. So essentially, we have this function g that depends on the point that we are looking at, well, the center of the ball, that we are looking at the probability that k intersects that ball, or, well, this could be xm, could be an approximation to x, a discrete approximation to that point x. And because of the rotational invariance of k, this function, this green function, is going to be rotational invariant as well. And it's actually just going to depend on what is its distance to the origin and its distance to the boundary of the ball. So our this term is going to depend on this quantity that I just wrote as dx. That is essentially what is the distance of x to the center. And the thing is that we know that our loop race random walk starts at the center. So the points that are close to the center are going to be more likely to appear on the path. And also depends on the distance of x to the boundary of the ball. So, well, we are just going to ask that x is at some positive distance to both the boundary and the origin on the ball, but that's okay. And our error is going to depend on that distance. But beside that, we have that this continuum ball hitting probability for k and 1-point estimate, of course, depend on this same function gx. And then they have the right, well, here we obtain, well, what we expect to have as the exponent, 3 minus beta. Here is the 1 over m, 3 minus beta, and our error. So the thing here is that as opposed to the two-dimensional case, in the three-dimensional case, what we can really work with is on the discrete. So the idea is to work on the discrete most of the time, and then whenever it's needed, essentially whenever we can take advantage of the rotational and the scale invariance of k, we go to the continuum, but that's the only thing that we can really use from the continuum. So to be able to go from the discrete and then to obtain results to the continuum, what we need is a continuity result. So this is kind of the key that allows us to really, to really go from this 1-point estimate for the loop race random walk to the ball hitting probability for its scaling limit. And it essentially says that if we are looking at the continuum, well, it should be purple. The probability that our ball hits, that the boundary of the ball, this is saying that the boundary of the ball hits K, but not its interior. So essentially, the interior has an empty intersection, but we have a non-empty intersection if we add the boundary. That would be as if our limiting object K just touches this fixed ball. But of course, that is unlikely. And what we show is that this happens with probability 0. So now that we have control that once our limiting object touches a ball, it really enters, then we are able to consider a discrete approximation. So that's why we can use this 1-point estimate for the ball hitting probability. And well, it's not enough to work for this for one of the goals of to improve our this result. The first was to get a better estimate for this 1-point probability, but we have a second goal that is related to the parameterization of the limiting object. So this 1-point estimates, sharp 1-point estimates result that I already showed you work for the first goal. But if we want to control parameterization by the Minkowski content, then we need to also consider 2-point estimates. So that is, if now I have 2 points different Z and W and consider small balls of the same radius around these 2 points, what is the scaling of the probability? Well, how this probability that our limiting object intersects both balls scales. So this is going to depend now on another function that is depends on the positions of this Z and W, but the point is that it rescales as 2 times 3 minus beta. So in a sense, this is not so far to just the product of the 1-point probabilities. It is kind of how this, how we work with this quantity. We have some asymptotic independence so that once we are at the right scale, the point Z and the point W are kind of far enough so that although the loop race random walk has its loops and it's really not Markovian, we can have some control and have some couplings with things that are almost independent. So that's why it's not so surprising that this exponent is just 2 times 3 minus beta. And well, for the this 2-point function is really needed for the limiting object on the continuum, but for the discrete we have a similar result with the same function g and the rescaling 1/m. So now this is something that it would have been better to explain a little bit earlier, because I have been saying Minkowski content all the time, and I'm not sure how familiar everyone is with this definition, but it's very simple. It's more simple than the Hausdorff dimension and the Hausdorff measure. So this is defined for bounded Borel sets. In this case, we are interested in R3. So my loop race the limiting object K is going to be a bounded Borel set that lives inside our unit ball. And what we do is that we blow up that set by some factor R, so it's like a little balloon around our object. And we measure the volume of that blow up of our set A. And this defines a content, a Minkowski content according with the parameter, an alpha Minkowski content. So here we are rescaling by alpha minus the dimension, which is 3 times the volume of this blow up. And then we take the blow up radius r to 0. And of course, this alpha Minkowski content is going to be non-trivial, only possibly only for the right alpha, which would correspond to its dimension according to this way of measuring our fractal sets. And we already know that the Hausdorff dimension for the scaling limit of the loop race random walk is beta, and it is also the right way to scale for the existence of, for the Minkowski content of the loop race random walk. So the Minkowski content that is non-trivial for the scaling limit of the loop race random walk is the beta Minkowski content. But then one needs to show that actually exists. And there is this recipe that has been used in a lot of works, mainly by Shinjili's research group and collaborators, which is essentially what I have been saying, that it's our goal to have control on the 1-point function and control on the 2-point function. So essentially, one needs to show that this limits exists, that we have the 1-point function rescaled by the parameter beta minus 3, where beta, would correspond to the beta Minkowski content that we want to show that it exists. And we also need some control on the speed of convergence of this limit, and as well for the 2-point function. And that's why it's important that for the results that I show you here, we have these sharp estimates, because that's what allows us to have not only the existence of the limit of Jx, but also control on this speed of convergence. And so you can see the theorem on the paper, on the reference that I'm going to show you at the end, and it's also applied, for example, for the existence of the Minkowski content for cut points of rounding motion and other similar random fractal sets. But essentially, it's just having a good understanding of these two functions. And with that, we can show that if we restrict to some nice box, just to be sure that we are not doing anything strange from a measure theoretic point of view, the intersection of this box and our limiting object K has a beta Minkowski content. And this is kind of the nice part that allows us to circle on our a scaling limit result. If I consider the limiting occupation measure that was obtained from the scaling limit of the loop race random walk, so remember that we were scaling according to this natural parameterization, and in this result of Shinjili and Shiraishi, they had a limiting occupation measure, and the result was in terms of that limiting occupation measure. Well, we can also consider the measure induced by the beta Minkowski content, the one that we show that it exists. Then there exists a constant, so that this measure nu is just a constant factor of the limiting occupation measure, almost surely. So that's what allows us to have this final result that really is this growing, well, it begins because we really use the result of Gary Cosma from 2007, and then the result on the natural parameterization of Shinji and Daisuke, and then we finish it in its full convergence without restrictions and with a nice rescaling in this preprint that appeared last year. So we have our growth exponent, the loop race random walk on the this ball with the rescale lattice, and we have our occupation measure, but it's just rescaled by m to the minus beta. So we don't have to write down a factor that depends on some probability that a fixed point is part of our trajectory. It's just m to the minus beta. So then we have that this loop race random walk parameterized by this occupation measure converges in this metric for parameterized curves that I showed before to gamma, which is the limiting object k parameterized by this measure nu that we show that it's parameterized by its Minkowski content. So then this limiting object is parameterized by a measure that is intrinsic to itself. So let me show you how we begin, this type of estimates. So I can show you how just the beginning of the proof of this proposition. So I essentially want to show you what is the role of non-intersections of random walks and why we can say that the loop race random walk is actually tractable. Because so far I have just said we can do this, and it all relies on the simple random walk, but with the idea of this, well, the beginning of the proof of this proposition, I can show you exactly how this appears. So you can see that here I'm looking at this fixed point, so a half 0, 0, and we have a very humble proposition. It's not the full result. So here I'm looking at the loop race random walk at scale 1/m. For some reason, I wrote km, but the m tells us that we are living on the discrete. Here I'm looking to some estimate in the middle. So the 1-point estimate for this loop race random walks is the probability that a point belongs to the path. But here I'm looking to something that gives me a little bit more of a space, which is the probability that a ball intersects this discrete path. And here we're saying that it scales this way and we can control the error. So essentially, and this is a very typical argument when we look at loop race random walk, we have our loop race random walk and it enters this ball of radius s. But the point, and the reason why it's nice to consider the ball instead of the point, is that we don't really have to worry about which points exactly this path crosses. It's as long as it's inside the ball, that's okay. So that gives us a little bit of a space to move things around and to compare this probability to something that is a little bit more manageable. So now I'm looking at the last exit point of the loop race random walk from the ball. And this is just the typical argument. We are going to consider the loop race random walk from this point onwards, and then it's the loop race random walk, but with its trajectory reversed. And actually, what we want to consider is not only the loop race random walk, but the simple random walks that generate the original loop race random walk. So I'm not drawing this simple random walk because it's it would be like, I mean, we would have a lot of loops. But essentially, like I'm just defining a point on which I'm just going to consider the original trajectory on its onward. But here I'm looking it backwards. And well, all the for this to still being a loop race random walk, we need to condition this trajectory that is going backwards so that it's a simple random walk that needs to hit the origin. And also we need to condition that it's not going to hit whatever comes afterward in the loop race random walk path, because this path is not going to be erased. So essentially, we are decomposing the loop race random walk path into a simple random walk and a simple random walk that is conditioned to not intersect. But we don't really care about what happens inside the ball as long as we enter the ball. So then we also look at the exit point from this ball, and so we don't really worry too much about what is happening inside as long as we have a simple random walk that is from the boundary of the ball and leaves. So this is a shorter path, so it means that this conditioning on non-intersecting the future is going to be easier to handle. And we only need this to start from the boundary of the ball and to reach the origin. And then something can happen in the middle, and then we continue our path outside, starting from Y. So essentially, this probability, the probability of a loop race random walk intersecting a ball, can be decomposed by looking at these probabilities of two simple random walks that are conditioned that this path gamma hat does not intersect, and it is just easier to condition that it's not going to intersect the full simple random walk that comes afterwards, S2, and we also condition that this sigma is not going to enter the ball so that we are not erasing what is happening inside. We somehow want the purple path to happen, and that this pink path is going to hit 0. So now the problem is that and the real work, so it's how to control gamma. But well, that's this is just the beginning of the proof. But if you see now, this is a problem about intersections of simple random walks that are conditioned to something, but and that is something that we can handle. So I realize that I don't really have time to talk about three-dimensional uniform spanning trees, but I just want to show you what is the consequence of what we prove for loop race random walk. So a uniform spanning tree for a finite graph is just the collection of spanning trees. I mean, a uniform sample over the collection of spanning trees. And something that is very well known, and hopefully it's not too terrible that I go quickly over it, is that, well, from this is for a finite graph, but we can define the uniform spanning forest for an infinite graph, set D, just as the weak limit of the measures over an exhaustion of finite graphs of set D. And then this is just a way to construct our uniform spanning forest. But we can also draw a sample of the uniform spanning forest with branches that follow that are loop race random walks. So essentially, this is Wilson's algorithm. So we have our vertices that we want to see how they span a tree inside the uniform spanning tree. And we just order them and start growing a collection of forests. And this could be forests because in principle, all these trajectories are not necessarily intersecting each other. But in 3 dimensions, they are going to intersect almost surely. So this is a loop race random walk that goes to infinity. And this is our first branch. And then we get another point, and from this point, we draw another branch and following a loop race random walk. So that means starting a simple random walk from that point, and this is a stop when it meets the branch that we have constructed so far. So we loop race the simple random walk. Essentially, the loop erasure is just this orange path. So that's the loop race random walk starting from this new vertex until we find what we have built so far, and we add that branch. So we continue drawing another vertex, and we consider a loop race random walk that is stopped when we find what we have built so far. And this is added to our set of forests of trees B3. And at the end, when we go through all the vertices, what we obtain is the tree spanned by the uniform spanned by these vertices of the uniform spanning tree. So this is a theorem of Benjamin, Lyons, Perez, and Schramm, that the algorithm proposed by David Wilson works not only for finite graphs, but also for these infinite graphs. And when we draw our trees with these loop race random walk paths, we obtain a sample of the uniform spanning forest. So this is just a very direct way to go from loop race random walks to this other object, the uniform spanning tree. And in 3 dimensions, this is actually going to be a tree. What we draw is going to be a connected graph. So we can think about this as a measure-rooted spatial tree. So it lives on its metric space, and we rescale, and that's how we understand the scaling limit. The rescaling of the distance by its growth exponent, the rescaling of the measure by the dimension of the space, and the rescaling of some embedding by some delta, parameter delta. And then we take delta to 0. So this is a theorem from 21 from my PhD, and we show the existence of the scaling limit. But the issue with this theorem is that we relied on these previous results for the scaling limit of the loop race random walk. So here we only had a scale over a dyadic distance. But now that we have the full scaling result, and this is essentially the idea of the proof, that we can just build with Wilson's algorithm our trajectories, and so now this is what I wanted to say. This dyadic scaling is from this previous the paper that appeared in 2018 of Shingeli and Eskeshirashi. But now with the result that we obtained, we don't have to restrict to dyadic scaling. Is just rescaled by this is going to be true for any subsequence. So to finish, let me tell you what we are doing now, and is that we now want to understand that we have the uniform spanning tree and it's embedded here. What we want to understand now is how the limiting tree is embedded here, and that sometimes, we can find some exceptional sets. So an exceptional set is going to appear when we have 2 branches. Here are just very close, but this is a tree, so they are connected far away. So we have leaves, that this is some sort of arm exponent, arm event. So we have 3 points that are very close, but here are not connected. They are connected far away. And this is something that is going to happen in the limit. So what we are working at the moment is to understand, these arm events. And from that, we obtain the Hausdorff dimension of this type of events in the scaling limit. So for comparison, the Hausdorff dimension of a leaf is 2 in dimension 2, and in dimension 3 is 3. For 2 leaves that are come very close, but are different points, and in the embedding, they just become the same point, and in the limit, this Hausdorff dimension is 5/4, and in 3 dimensions, it's 1 plus beta. But if we want the Hausdorff dimension of a point in the middle of a branch, in 2 dimensions is 5/4, and in 3 dimensions is beta. And something that we are currently trying to obtain, so this is something that we know, and this is something that we are developing, is that in 2 dimensions, something like this cannot happen because of the planarity. So this Hausdorff dimension is 0. But in 3 dimensions, it could happen, and we have a bound, an upper bound, and what we are missing is the lower bound for the Hausdorff dimension to be 2. And then we also consider a branch and a leaf that comes very close to the branch, and in 2 dimensions, this Hausdorff dimension is 0 and it's actually empty. But in 3 dimensions, we think, and we have an upper bound, but we are missing the lower bound, that the Hausdorff dimension is 1. Okay, so I apologize for being over time, and this is that I want to end. Thank you.
Thank you very much, Saraí. So, okay, we have a lot of people clapping. Questions?
I have a question. The function g of x that appears in the heating probabilities, do you know how it scales with x?
We have an asymptotic from when x goes to, when x goes to 0 and when x goes to, when the length of x, sorry, the norm of x goes to 1. So essentially when it goes to 0 and when it goes to the boundary. So, and well, the exponent of scaling is different, but we do not have more than that. That's all that we know about x. That is continuous, that is rotational invariant, and some asymptotics for this function g, and when x then goes to 0, and let's say when x goes to 1. But that's all.
So yeah, I think one of the main results you presented was that when you have this convergence in dimension 3, you can parameterize the discrete path by the counting measure and the continuous object with the Minkowski content. And is it true, and was it known in dimension 2 or?
Yes, this is this convergence in the natural parametrization of Lawler and Bigland. So here it's the parametrization for SLE2 is the one given by the Minkowski content.
Okay. No, and another question I had was that it seems natural to think that this beta should increase with the dimension. Is there any hope to prove that beta is larger than 5/4 in dimension 3?
That should be true, but it's natural, but it's not something that we has been done yet.
Okay.
But
Thank
yes,
you very
you're
much
right.
for the talk.
There is a question in the chat, Saraí. Maybe I can read for you.
An intuitive explanation.
Yeah, about an intuitive explanation for the exponent beta of the one arm.
Well, here, the comparison here is that we have I just want to make a distinction. So here I'm just looking at the dimension of a point that belongs to the arm. But I believe that the question is about this one above, that is that we have 2 leaves that are very close to each other, and in the limit they become 1. So the one below, the one that is just inside the branch, it's really just because we are looking at the loop race random walk path. But the one above is a little bit more interesting because this is 2 loop race random walk paths that manage to escape from one another. So essentially you have that a microscopic scale, you reach some macroscopic distance from one another. And this is sort of comes from a escape, the scale, like escape exponent for the loop race random walk and the simple random walk. So really, I mean, the explanations are in terms of what is the probability that a loop race random walk or two loop race random walk manage to escape another loop race random walk. So that's where these explanations come from.
Okay. Are there any more questions?
I have a question. It's a very simple one. Just how is it proven that beta is more than 5/3? So where does the 5/3 come from? And like, yeah, how do you prove that it's not Brownian?
Yeah. This one.
Yeah.
Actually, I think I'm going to owe you that because I don't remember like what is the argument. But something that I can tell you is that for the bound, you don't really need to. You don't really need to show that the growth exponent exists, and that's what actually Greg Lawler did. So before this existence result, you can just consider the lim sup of these quantities and show that that is going to be, well, the log of this divided by n, the lim sup of that is going to be smaller than 5/3. And the argument is going to be something about intersections of simple random walks. It always comes down to that, but I'm going to like owe you that on how it is done. But it's not that difficult. I'm going to study it for next time.
Thanks.
Could I ask another question? In the dimension d equal to 2, how to see that the growth exponent equals to 5/4?
That's that's more complicated, but better because it's a combinatorial argument. So like there's this, the loop race random walk has this connection to the uniform spanning tree by Wilson's algorithm that I very quickly overview. And then the uniform spanning tree in 2 dimensions has bijection to dimers in 2-dimensional lattice or this. And then this, there is a bijection temper. Well, I'm not going to pronounce correctly the name, but the point is that then Rick works with this, counting these dimers, and then the asymptotics of that implies something about the uniform spanning tree, and from that he gets the growth exponent. There is another paper, so well, that's not something that I know like extremely well, but I can tell you that there is another paper by Robert Mason, who was a former PhD student of Greg Lawler, on which he shows the existence of the growth exponent for the 2-dimensional loop race random walk is 5/4. But without knowing that the scaling limit is the Sham-Loeffler evolution, and that you can also use this bijection. So essentially works this growth exponent estimates just with by looking at the non-intersection probabilities of simple random walks. And that's a work that was, and he also, well, Robert Mason did his PhD with Greg Lawler, and then he was a postdoc at UBC with Martin Barlow. So he also worked on that, on this type of problems with Martin Barlow. So there's like the 2 or 3 papers of Martin Barlow and Robert Mason, on which they do everything in 2 dimensions, but without using SLE theory, just simple random walk estimates. And then that's something that was very, very useful for us in the three-dimensional case, because their techniques, we could essentially use their core arguments, but then find the equivalent estimates for three-dimensional simple random walks that they use for two-dimensional simple random walks. One of the problems is that an estimate that they use in the two-dimensional case is this Bernoulli estimate, which is not true in 3 dimensions. But then we can, Artyom Sapochnikov and Eski Shiraishi has some type of Bernoulli estimate. So essentially it's control on the capacities of our simple, if you have a set of a given capacity, also the probability that the simple random walk is going to intersect that, and then you control the capacity of the loop-based random walk, this type of arguments. So yes, the original proof for the growth exponent is very different, but there is this alternative proof that was very useful for us. So that's what I can tell you.
Okay, thank you.
Okay, no more questions. Then let us thank Saraí again for a beautiful talk, very beautiful talk.
Gracias, Saraí.
Gracias. And I hope to see a lot of you in Montevideo, like in March.
Start.
Yeah.
Yep.
Bye. Thanks.
Bye. Thank you.